Okay, one of the things we really would like is to have a theory of turbulence, so a fluid dynamic model for how energy transfers as it moves through a wave, but moves through the scales. We have good dynamic models for how it moves through a wave staying on the same scales. But here, when you break up into new swirls and then new smaller swirls and so on, we want a story for why they break up into those different scales of swirls, right? We want a richer understanding in our head, a model for the action that's occurring there, basically. So that's a really nice one. Let me jump out of physics and say, in mathematics, what would you say is the main goal of the entire field of mathematics? It's bothering me.
Figuring out what this x, y is.
Yeah, or in more general, the field. So in mathematics, you have a field on which you can do operations. You learn the simple connective operations from the get-go right in school, plus and minus, multiply and divide. Okay, but you're very abstractly introduced to these concepts, but it's not so clear what model it applies to, right? In mathematics, the goal is to get some clarity on what is the field on which we're doing all these operations. Why is it true that these operations we've found in the world are there? We're not doubting that they are. That's a scientific investigation. Those are all facts with error bars that we have confidence on what the world is. But we want a story for why, right? So in math, we want a field theory. And I'm going to go ahead and say again that when you have a satisfactory answer to the goal there, you are in possession with a mental image that's a geometric model that does the same thing as reveal the inner gear work of a clock, right? And the clock in this case is what? An atom and the rules of quantum mechanics. Okay, so the thing we're trying to crack open and see with our mind is how the internal parts of an atom fit together, why they're there all to begin with, and so on. We want a geometric story. Okay, it's very similar in ways here. There's a lot of crossover between what you're looking for, right? In physics, what are we looking for?
Everything.
Yeah. It kind of defines the field of physics, right? Theory of everything. What do we mean by that? There can be a lot of subtle distinctions in your meaning for the theory of everything right now, right? What's the general claim here? What's the goal? If you had a theory of everything, what does that empower you? How does that change you at all?
I think maybe one aspect of that is unification of general relativity and the quantum mechanics of the micro scale world, right?
Yes. So there should be some aha moment if we have a theory of everything that goes from quantum mechanics makes some hardly any sense at all, but it's its own system, and general relativity makes a story about the world that doesn't go along perfectly with quantum mechanics, right? But then there'll be a new story that says, of course, these two parts of this other real thing. You'll have an in-place structure for how things are. Okay, that's helpful. For those of us who have been spending time trying to get that picture, that's really helpful, right? But what if you didn't know to look for that picture? What else does it do for you?
Helps give you a better idea what the heck's going on.
It helps you see more, right? We don't see objective reality. No one does. The goal is to wake up more to the ingredients of reality, interact with them so you can figure out how to think of them, and then you see them the way you currently know how to think of them. The ingredients you haven't even discovered yet, you don't see. Right? Nobody saw electrons in their mind. They never thought of applying them and using them in the world until electrons were discovered, right? Until it was a concept.
And it also allows you to engineer things you can't imagine right now.
Yeah. That's this big, huge superpower. Using electrons again as an example. The things we now use electrons to do are mind-blowing things, all things that weren't imagined as things you could do as a human being before that mental construct became available. Okay, so the evolution of our internal mental construct is what I think the goal of science is, right? No matter what level you're at, you're trying to move to an even better story. You're trying to make yourself aware of ingredients you've missed so far that require a better story. not just sitting happily in the story you're already in, right? Because you're aware that you're only able to physically see the experience of sight. It's only available to you to the level in which you understand. To me, that's a mind blower. But in here, there's a lot of overlap of what we're really looking for, right? We're looking for explanation of order, of logic, how it's built in, right? How about in chemistry? The table, or the periodic table of elements, right? It focuses on just that part of the story. It has noticed a pattern in the world. The field of chemistry is a conversation around a pattern that exists in the world, and how you can use that pattern to do certain things, right? And the more you become aware of those built-in patterns, the more it makes sense to you to guess how to try to do another things, similar things. All right, the thing is that's important about the periodic table of elements is that it's periodic. It has features that repeat a certain number of times over and over. I mean, you multiply by one more whole of that number over and over and over. Another thing is that there's rows and columns. So they repeat in rows, but then there's a repeating pattern in the columns also. So there's some connection, and we have a block chart periodic table of elements. There's many actually periodic table. There's many official ways to try to take the properties of atoms and arrange them into a periodic table of elements. Okay, and you should think of all of them as ways to look into the structure of what's going on there. We have an official one that we've settled on, and a lot of people have argued to get to that one. But there are many other ones that were runners-up that really deserve your attention too. Okay, but the point is, the thing is, this conversation is about trying to find the pattern, trying to understand the underlying structure that causes the pattern there. Okay, it's really the same sort of search, but it's narrowed the pattern that we're talking about, right? In philosophy, we could go back out and say we're trying to maximize the scope of the patterns we're talking about, right? And it can help to do both, to narrow and focus in on one and really get the details right there, or to try to keep in mind all the mysteries you're trying to balance at once. So from there, let's focus a little more on physics. We are after a story for why the electron has the exact charge it has, the exact mass that it has, right? Why it has the spin that it has. All the properties of the built-in features that make up our world, all the things that make electrons, protons, and neutrons do the dance they do, right? And the other particles. All of those features in physics we have found very, very reliably to show that you can build everything in our world from just that list of features. This is the pattern in physics. Instead of the periodic table of elements, we have a list of fundamental ingredients in a standard model that everything is built up from. And how are they built up from, those ingredients? If you think of the ingredients elementally as the pieces of mass and the pieces of charge, those mass and charge pieces are put together into the actions we now call atoms, right, under the laws of physics, using very specific parameters called constants of nature. That's what we found. Now that's a story that is a start to a story, just enough to make you really interested in where it goes from there, but that's where we're at so far, right? We have a list of fundamental features that everyone around the world's different languages, all the scientists all around that set up labs to test these things have come to a measurement, a better measurement, a way to make a better measurement. They're making discussions daily about how to make better measurements for these, trying to imagine a way to get a better one than we currently have so we can be looking closer into the world and potentially understanding more about what that feature actually is. But to date, all of the features that the constants of nature represent are contentless. There isn't an explanation in the physics story for why they have that scale, that exact number. It's just a thing we've noticed and reported. We've measured it, right? And we know how well we know the number. We even know our confidence on the number. The only way we're going to get to a coherent, viably penetratable story geometrically of what's going on there in the constants of nature, the things that are holding the pieces of atoms together and making them do the dance that they do. All the things responsible for that. The only way we're going to get there is to look at those constants and compare them objectively and look for the patterns that those objective comparisons hold. The same way we do in mathematics, we have a whole branch now called group theory. right? It's looking at the inherent symmetries in modular forms, in anything. We're looking for the inherent built-in symmetries. And you can understand those symmetries as logical constructions, logical restrictions also, right? So the symmetries are very important to us. We want to understand what inbuilt symmetries are there in the constants of nature, because these are the mysteries that are holding the things we believe the world's made of together. We want to have a picture for what they are. And we know that we're not going to get there very fast if we just task everyone to make up an answer and then we'll see which one sounds best. That's not a very productive process. The best way is to task everyone to look at the data points, look at the measurements, compare all the measurements, find ones that you think are more comparable than others for whatever argument, but look in the details so you can make that argument. Find which dimensions they're composed of. Compare ones made of the same dimensions. Compare ones always made of different dimensions. Ask lots of stories about it and see if you can find any kind of symmetries built in to the measurements that we've made about what the reality is so far, so we can continue the story. Okay, so that's our process, and we've been using Wolfram Alpha. Wolfram Alpha has a lot of advantages. It's a superpower, I think, unrecognized so far. Chat GPT is a new superpower on the planet, right? Wolfram Alpha offers a superpower in this direction. If you feel under a cloud of ignorance when it comes to mathematics, you don't know what even to expect, even if you came to a question. Oh, I got a question, but then your gears don't go anywhere next. You don't even know how to guess what would happen. It's just a question. You know, you'd like to know the answer, but you have no hope for try. Right? There's nowhere for you to go next. Wolfram Alpha is the place you should go. If you can ask any mathematical question, it'll spit out a whole bunch of possible closed forms, things, arrangements in logic that get you to an answer satisfying the question you just asked. Now, that's different from telling you the answer. You don't know if any of those are the answer. Maybe you can ask a better form of the question to get a better answer. But the point is, it gives you possible things that could be the answer. You went from being completely unable to guess on this essay question test to having a multiple choice question test. That's what you did. And now it doesn't mean your next step's going to make you right, but it means you have a next step to try. And if you have enough ambition, try them all. And it does mean you're going to get some right. Right? See, if you put more effort in now, you can keep going and find more and more patterns, find more and more simple things to find. And at no point are you thinking, that's it, I have the answer on any of these questions you're asking, right? You're thinking, I'm looking at something that satisfies what I asked for, and it says there's an arrangement, a stamp into logic like this. What is that? And you can ask questions. You can click on any of the constants that pop up in those arrangements, and if you've never heard of them before, it's just like falling down a wiki hole. You're going to go down and discover that there's somebody's made a discovery in geometry and logic built into reality somehow, and they discovered that this connection exists, right? The thing you just got exposed to. So it's every discovery in mathematics is that. It's a discovery in logic, a discovery that somehow exists in reality. It's a new feature of the world. All right, so that's our process, and since we have error bars, we can really narrow down, restrict a lot of the possible answers that pop up, right? So let's discuss a little bit about the error bars process. When we report the science numbers, at what size, what we report error bars with them are confidence range, right? So that's confidence scale of 1 from the report. How far off from that measure can you be off and still be considered the story in science?
Maybe a couple sigma, depends on the measurement.
It's officially at 5. If it's 5 sigma off, 5 times the error bars. I mean, if you're reporting accurate error bars, but someone has an explanation that gets you to 6 times outside the error bars, then you would say, these numbers require different stories. Okay, that's officially.
1 plus or minus would be 0.006, is that what you're saying?
Let's say.
If you have an error of like 15,
Yeah.
basically 5 would be like a 75.
Okay,
Like
that's what I meant.
because usually you'll have parentheses and you'll have a number.
Okay.
Yeah, here we report a number, I can get times 10 to the negative 3 or whatever. Okay, that's a scale, but the error bars are reporting to an error on the last two digits. So 72 can be plus or minus 15 on there. And if you're 30 away from 72, then you're sigma 2, right? If you keep going to counts in 15. So if you get more than 5 away, then we say for sure we have to think of these as different stories. Now, a lot of people are very uncomfortable as you approach 5. So it's more like you're very much more comfortable with less than 4. You're very much more comfortable with less than 3, right? Around 1 is what you're reporting. So you don't need to go less than 1, but yeah. Okay. These constants of nature are the things that we're using to define the dimensions themselves. These constants give us the conversation of the dimensions, how the interactions built into the dimensions. But we define the dimensions based off of these measurements. Okay? So since we can define it too, the definition gets to swing, think in your mind too. There's an error of our measurement, but on the right-hand side, there's a definition of this, how you're changing the definitions. If you think that one measurement over here was more accurate, this one here, and so you rely on it to swing things, but it was off, then you just swung the whole picture off a little bit in the definitions of the dimensions and how they fit, right? So we're having to pick the definitions at the same time, but we're using these measurements to do it. So our last swing had a swing of 3.5 sigma in it. So by the last time CODATA changed the definitions, like, okay, we have a better measurement set now, so let's try to go through them and figure out where we're pointing all these things for the definitions to come out. It changed 3.5 in some of the places, okay? So that, for me, tells me this is really the range that I should be looking for. Okay, up to 5 is allowed, but 3.5 is where I'm trying to stay around and under. Okay.
Quick question. So, Stab, what is the significance of 14 significant digits?
Should I do that now?
You can go ahead. If you have it planned out, that's totally fine.
No, well, I do, but I have a different answer than I've given you before that I think is a faster way to approach the insight there, but I think I'm going to build up to that first.
Okay. No.
All right. But there's another one that ties along as you keep in your head before I get there. There's another significant thing that I've laid out that we didn't ask is, what's the significance of base 10? I wrote those things in base 10, right? Times by 10 to the power of something. And the digits had up to 0 through 9 as options. So it was base 10 number. So why is this significant in that? Now you might have the attitude, well, if there's patterns to be found in physics, then just pick any base and you should be able to find patterns, the symmetries built in, right? But you might also think, if things are breaking up into quantized numbers of pieces, then the most fundamental breaking up of pieces kind of determines the base of the logic. I guess I am kind of going into it now. Huh? If you have a system that's internally dividing, creating boundaries, but if any system that's just breaking up into pieces, smaller and smaller pieces, but more numbers of pieces, the most fundamental pieces of the system, if it's a quantized system, so it doesn't do this infinitely, okay, it doesn't go smaller infinitely, there's a bottom to the system, then that means that bottom has to set the most fundamental base in the logic of the connections. Right? It is not obvious why?
No.
Do you guys or not?
It must set the fundamental base, but not
Yeah.
if it's 10.
Oh, okay, good. Yes, okay, good. Yeah, because I haven't said that part yet. Okay. We're going to be proposing a geometry that makes sense of the 5 dimensions in reality, right? Time, space, charge, mass, and temperature. So these are the 5 dimensions of measure. These are the things you can go out with a ruler or a thermometer. You can devise a way to get an accurate scientific number attached to the thing, right? Okay, so these are the 5 kinds of things in the world. And everything else, according to our story in physics and chemistry and so on right now, everything else we've observed is built from these 5 ingredients and the fixed relationships that are in nature or in atoms with these 5 ingredients. So what we want is to go from a picture, from a vague word that fills in here. Each of these are mysteries, right? Complete mysteries. What is time? That's a really deep question. right? But it's also kind of a very vague sense thing in the way that we talk right now. We don't have a lot of clarity even in our language about what time is. But we want a geometric picture for time. And we're going to propose a story in which these are in sequence, sequenced as bases of partitioning created by a geometry. So we're going to have a geometry that breaks up into different sizes of rotations, different radius, so different size circle, okay? But just different sizes of rotations, and each rotation counts as a base in the geometry, a base in this persistent form of logic that maintains a certain connection and exchanges always happen a certain way in it, okay? So with our base being 5, we can say, let's attach this, let's assume that these 5 bases come together to make the simplest 3-manifold there is, called the Giesecke manifold, okay? All right, well, that isn't enough, it turns out. If you make the Giesecke manifold, you've just made a closed surface, right? But that surface will then completely dissipate. It'll go completely away. You didn't have enough energy to maintain it. You just had enough to make it once. Now, to close a surface, it's pretty easy to make the leap that once you have a surface that you can create, you can use that same surface a second time to bound the first one. Put them inside out each other, right? So you can double cover a closed surface and use it as a boundary, which means the smallest possible persistent boundary would be the double cover of the smallest possible 3-manifold, closed 3-manifold. All right, and that has a name in geometry. So this is the smallest closed manifold in geometry available, called the hyperbolic figure-8 knot. Okay, so we're going to start in our story with a system that ultimately projects out, well, let me start a little further back. Imagine we started in a region of the void that's infinite. There's no boundary, no matter how far you go out or in, okay? And by infinite, I mean that what's filling this infinite void is a collection of random waves. There's no persistent action. If you were to look one place and come back later and look there, you wouldn't see the same thing. There's nothing persistent around, okay? That's different from being entirely empty, yes, but it's empty of identifiable character. You can't point to any feature in the system. Okay, so once we've formed, we want to start an infinite void with just randomness, random noise in it, right? We want to ask, what's the minimal way to construct a self-balanced geometric universe in that void on any scale? We're just asking what's the simplest way to do it, okay? And by simplest universe, I mean whatever distortion you make to form a boundary, and that boundary is doing things, so think of it as acting like a speaker and pushing out. There's going to be some limit, though, in which it doesn't push out enough to hold out. Everything outside that boundary, out that spherical shell, will still be in the random noise. But everything inside the spherical shell will agree on a logic structure, because it's decomposing a certain way and everything continuing to flow over and over in that geometric form. So the built-in structure of logic within this infinite universe of randomness to now a structure. But what we want to know is, what's this minimal possible universe? It's spherical on the outside, fine, but what's all the detail on the inside boundary moving around that's projecting this sphere? First of all, note it's finite, right? That's a big detail here. So if it's finite, and we're going to break up into a finite number of pieces, there's going to be a gap on the inside that has a finite volume, right? And now let's pair what we were saying before. We're going to pick the smallest possible universe as the one that's sitting on the internal volume, the amount of volume you fold around on yourself to form it, so the gap on the inside represents the hyperbolic figure-8 knot, okay? Now what we want is a picture that goes from how do you distort internally from the hyperbolic figure-8 knot to the externally, the sphere out here with the quiet, boring surface and all that internal balance going on. What are all the actual details from the smallest to the highest geometric representation of this structure? That's what we're after. Now, the good news is it's finite. So you don't have to be scared of going forever for steps before you're going to get to the answer. There's going to be a finite number of steps. Other good news is the system works much more efficiently if it's fractally bound, meaning if it's self-similar in the transform it uses from scale to scale. If it's a completely new transform on each scale, then it gets much more complex as a logic system. But if it's self-similar, you re-stamp the same logic structure over and over and over, right? So it's even simpler as a logic structure. All right, so this is the picture we're going to try to fill in now. We didn't have before. So this is really exciting to me. Let's start with, we got our huge, well, a huge doesn't mean anything yet. We're in an infinite void. There's nothing you can point to as a reference, so there's nothing you can use as a scale. There's no meaning to scale yet. But when our universe gets put into existence, now suddenly there are scales. In ours, there's going to be 5 actions responsible for this region of balanced logic. These words making sense? Yeah? Okay. So let's put in a point for the center. So I can imagine this zooming in towards the center. Okay. As we zoom through this, we're interested in describing what it looks like now. On its largest scales, it looks like a sphere. That's pretty easy to start with as a mental picture. But as you zoom in, we're trying to make it so that we see the picture of how these boundaries inside are keeping this sphere. So it's not a magical sphere that just came into existence and has no reason. It's always being maintained by a structure of an internal boundary that's forming and wrapping into different geometry that's stable. Okay? So this is just the most outer expression of that stable distortion. Right, well, when we zoom in enough, what happens is we get to a scale where there's a torus boundary. Think of the fluids in motion now, and that boundary exists as a torus, meaning if you're part of the fluid, you never will cross the boundary. Your motion is always going to be, if it's near the boundary, going exactly along it, right? So none of the fluid crosses this new boundary. So it's a torus boundary is the first scale decomposition of this external projection. Now let's zoom in on the torus. Okay. If we zoom in the torus, what's going to happen is we'll resolve this torus into a ring, and another ring, and another ring, and another ring.
Those rings intersect with each other, though, don't they?
You're absolutely right. It's going to be
It's hard to
much harder to draw. But let me make my torus hole like that, and then say there's a ring like that, and then a ring like that, and then a ring like that, and a ring like that, and a ring like that. Yeah. Oops. So there's a bunch of rings connected in the hop link way, meaning we have each ring's a torus, like a loop. Okay, think of it as metal. But then when you're putting together loops, you always make sure you cross the new one before you weld it, okay, through each of the previous loops exactly once, right? So this is a looped system. It's a loop that decomposes into loops, that decomposes into loops, that decomposes into loops. Yes?
Are those 7 rings there?
There's going to be 8 rings there.
Okay. Cool.
The mass one. This is the mass boundary.
Okay.
So the first boundary in the fluid that shows up is the mass boundary, and it just presents itself as a mass boundary, a ring from the outside. But if you zoom in close, it's actually 8 smaller rings that are wrapped around into the form of a ring.
Okay.
Or on that scale. I shouldn't say actually. It depends on what scale you're looking at and what features you really get from this thing.
Did you start with the mass boundary because the outer sphere is the temperature?
The outer sphere is the temperature projection, yes.
Okay.
Which goes to 10 to the 32. So I'm extremely warping the scales in the drawing, right? This is from the center to out, this is 10 to the 32. From the center to this scale is 10 to the negative 8. I really went through a lot of logarithmic powers from here to here, okay? Okay, but this is the bulk that we're in. If we didn't have this logarithmic connection that we're explaining, then we wouldn't have much space to do stuff in. Great. All right, you can probably guess now, what's the next step? When you zoom in, you check out one of these circles, one of these, I drew them like ellipses, but toruses, okay? You zoom in on it, and it's actually made up of another whole number of tori stacking next to each other, right? Going around a necklace.
And they would represent the charge boundary.
Yeah, the next step down is the charge boundary. Yes. Yes. So it's the number of scales you step down into the actual boundary that determines how many of them are in that ring, but it's always going to be a whole number. And we go from the mass boundary has 8, the charge boundary has 18, the temperature boundary has 32, its inverse boundary is where it's being fit together, so that's under here. And then the space boundary has 35, the time has 44.
Okay, I'm
Okay.
confused on one thing.
Yeah.
The temperature boundary has 32, but I see 1. So where did I go from?
The temperature boundary inverse, this is the temperature projection. The boundary that is connecting with these things moving around, the torus boundary part of it, is 1 over the 32. So it's dividing the pieces into 32. And it's exactly the fit of this one and this one together that make it. Let me show you.
Yeah, I'm still confused.
Let's see.
Okay, most of the roles.
Okay. So when we have a torus, this is a cross section kind of. The torus comes up around here and goes back around here. Okay. The boundaries of the torus are of 2 kinds. We got this one that you can't cross if you're part of the fluid obeying this balance.
So you're either on the inside or the outside.
Yeah, this torus means that you're either inside this torus or outside it. There's a boundary you have to be in or outside of. Great insight. And then there's another one here. There's a boundary line in the fluid. If the fluid's twisting to make this torus, then there's another place where everything got twisted inside out. This exact place in the middle. This on-cone structure always exists in relation with this torus structure.
Now, shouldn't there be a gap at that point in the torus?
Yeah. Well, actually, more details we're going to throw in. I'll put color with these. So this structure has a balanced ruled surface. Think of this as a bowl, okay? And it comes with this one at the same time. And it comes with another ruled surface. By ruled surface, what do I mean? This one's more like the shape of a catenary or a, what did we call it? Nuclear power plant shape. Okay. Right. So these ruled surfaces, they're 2D. If you're on them, if you get close, they look Euclidean. Okay. But most importantly, by ruled surface, we mean that they're a 2-dimensional structure on which the operations of x and y in math all work. That's saying something, isn't it? That's the why. Why would that be? On this surface, anywhere on this surface, if you move along that surface, that's a movement that is perfectly validated by all the operations in mathematics. Doesn't contradict any of them. In fact, it looks like it just is it. Okay, same with this one. But notice that you can't really confuse the red and blue ones. Oh, and what are these? This is the surface between the 0 bounds. The surface put into balance by this action and this action. It's at this point, this is the dead zone where everything was tiled together just right by the things acting on both other sides. I think that's a new way to say it, but right? You're building a 2-dimensional logical structure, the surface of a 2-dimensional form, and you're doing it by tiling together actions from inside and outside, and they both push, and next piece of the tile, do it again, do it again, do it again, do it again. Okay, so we've got a lot of details now. We've got our intersection 0 cone, or the division cone of any torus, or even Clifford torus. This immediately pictorially should map to Clifford algebra for anybody who's familiar with the structure of algebra. This gives you the structure of Clifford algebra, the structure of the algebra you've learned. Okay? Any torus size, any geometry that does this twisting in the middle of the cone on cone. Now, if we back up a little bit and just look at some of the properties of this 0 bound in this balance, if you slice it, so we're going to make it easier to talk about it by reducing the dimensions we're using at a time. We can now take a plane and slice the cone. Okay, and you can slice the cone so that you're slicing through the top and the bottom one at the same time. There's lots of planes you could slice through that way, right? But then there's a limit. If you come out too far, you can only be slicing the top one or the bottom one if you're tilted too far, right? So there's cutoffs into our slice descriptions of this thing. So let's talk about what those different slices tell us. If we slice it in a way that goes through the board this way and is perpendicular to the axis of the cone, then we'll guaranteed for sure we're going to be either on the top cone or the bottom cone. Or I guess you could be the middle. Those are the options, right? But you can't be both cones at the same time if you're at that angle to the pole, right? And you'll be cutting through the cone, forming a boundary that looks like what? A circle. All right. So slicing perpendicular gives you a circle. If you slice so that you're parallel to this boundary or this boundary, doesn't matter, right? You slide around and it becomes the same. Then however you're slicing through the top or the bottom plane will be a parabola. If you're slicing so that you're cutting both of the triangles at the same time, then now you're a hyperbola. So they're all the same. They're just two-dimensional reduced descriptions of the same balance, but their features are built into that balance, right? Hopefully you can see them all. I'm just slicing different angles. And this is the division boundary of any torus construction. You know, go down low in the pool and blow a ring of water and have it go up. In the middle of the ring of the water, you're going to develop this cone boundary. You can't get the torus flow to be holding a ring together without getting the cone boundary, basically. Okay, and here's the thing. These are the zero boundaries. That's the boundaries you can't cross, put into the system. And this one too.
So the plasmoids are self-contained structures of plasma. So it's self-contained, so it has the stability. So it's sort of, okay, so there's something that is resonant with the self-contained feature with the stability. They're hold together by the magnetic fields. They're often found in astrophysical phenomena as well, such as solar flares. Okay, so I'm not sure. But apparently, this kind of structure is pretty common. I don't know whether it's pretty common, but it's been seen in other fields.
Yeah,
Plasma, even at the cosmological field. I think I read somewhere, like some people even came up with, this is not the common understanding, but even they say that at the core of a black hole, you could model it with something like a plasmoid kind of the structure. So anyway, so I just mentioned that it sort of like give me some, okay, that's kind of interesting.
I think also general relativity is this structure.
Oh, okay.
Right? It's the four-dimensional hyperbolic structure. This is four-dimensional. You create the blue surface, the two-dimensional ruled surface. At the same time, you create the red surfaces, right? The two-dimensional ruled surfaces. So you put 4 dimensions of ruled construction into the world with this balance. This is the exact balance Einstein said that general relativity looks like, right? Now we're getting to more clarity of a picture of what that means to say hyperbolic geometry is this form, and that's why it's four-dimensional and so on. But go ahead.
Well, just to piggyback off of what Tony was just saying there, you might find this interesting, but apparently Princeton, for their confinement attempts for fusion, they have something called the naughty nautatron.
Oh, okay.
It's literally using knot-like geometric structure. I think they're currently using a trefoil knot in an attempt to do said confinement. Apparently, it seems to be working pretty well for them. So, just a little tidbit I thought was kind of cool.
That is cool too. All right, so a feature we didn't talk about yet in this construction is the space between the red bowls, those surfaces. This is the mass gap in hyperbolic geometry. If you were to squeeze them closer towards the center of the cone, make this gap smaller, then you'd be changing the angles of this cone so that its arms go out like this. And when you get all the way down to where the cone or the red surfaces touch, the mass gap goes to 0. Okay? That construction now has the cone go all the way like this, dividing into a sphere and a sphere. One below and one above, right? So that's a limit to infinity. That's the hyperbolic construction if it's an infinite form that you're hyperbolically constructing. We're not interested in the infinite one. We're interested in the smallest possible quantized one. The small one's first of all going to mean non-infinite, but we also want the smallest. The simplest, we also imply by smallest, okay? So that is going to be some magical exact scale. Any scale you pick, remember, is going to give you cone-on-cone construction as a division boundary, which means you're forming a torus boundary out around there between it, and you're forming logical two-dimensional surfaces that are constructed, put together by all those actions, where these transforms all work.
So we're looking for an infinitesimal.
We're looking for an infinitesimal, not just as a word, but as a picture, as a dynamic form that we can ask things about and continue with. Great. So this mass gap refers to, well, if you change the mass gap, you get any other kind of hyperbolic construction. So hyperbolic geometry requires one more bit of information. What scaling parameter is important in my hyperbolic construction? That's it. You just need to set the scaling parameter. So in our model, we're going to have that scaling parameter be equal to the Planck mass, the value that we found from the constants of nature that's the limiting value of mass in reality. Whatever this dimension of mass is, we're going to match it right to our story so that the actual external size of the hyperbolic geometry in our external projection is set by that Planck massing scale. Okay? Let's leave that one up. So I want to characterize this balance right here in algebraic form, using algebra, using mathematics to say something about this. And we want to put in the scaling parameters so that we can then kick out more information to pay attention to in the structure. Okay? We want to notice more by being more explicit about what's going on. So I want to start out, well, first let's do a little side jaunt and talk about this graph, y equals 1 over x. This is known as the graph of the hyperbolic logarithm. The graph looks like this, something like that. So that would be 1, 1. Okay, what's interesting about this graph? Well, it turns out a lot of things. If we start at point 1 on x and drop a line straight up, it hits the point 1, 1, and that's on the graph. So we can have a unit square that touches the graph at this one point with an x coordinate of 1 and a y coordinate of 1. Now, from this point on, the graph gets smaller and smaller, or it descends, okay? But it asymptotes, so it doesn't always go faster and faster down. It cuts off at some point, or it's approaching some point. The question is, let's look at the rate of how the hyperbolic logarithm approaches infinity in the x direction. And let's look at it in a way that we're counting areas of 1. So our first mark was this number 1. We're always using 1 as a reference, right? So after 1, we've got 1 square unit under the curve touching that point. If we want to get another 1 square unit, how far out do we have to go? It's not 2, right? It's be 2. If it was 2, we're missing part of the square. There's some area missing. So we have to go further to get enough area to make up for that. So somewhere over here, let's pick it here. Anybody know what the number is? E. Great. E. So if you go out to E, you've now got another 1 square. You're now counting 2 square units. Okay? How far do you have to go out to get to 3 square units? E squared, yeah. And then E cubed, and so on. So in the hyperbolic logarithm, in this equation, we're just as simple as one thing equal to 1 over x. This connection equation has a very interesting built-in relationship between 1, the unit, and E. Square ones and E. That's very interesting, I would say. So that's built in. We can also start, or that's built into the hyperbolic logarithm into its structure. Let's start with it as our first piece that's going to be representing this connected form, and the opposite we're going to have its piece and its opposite. We have an inversion here. We're going to include both. And the third piece, let's pretend that our cone was infinite. So our cone proportions, this one is much bigger until they get to infinity, or our mass gap is 0, so that now we're just dividing the world into the infinite hyperbolic structure. But then I would say, there's our volume we're dividing, and this whole thing is going to be equal to 1 over infinity. In this sense, I'm going to let that be the limiting thing that goes to 0. Okay? So we're going to ask, where are the 0 bounds of this infinite hyperbolic construction? And after we familiarize ourselves with what this is talking about, then we're going to go ask, all right, we don't want it to be infinite anymore. We want to quantize it. And what does that change in the story? Okay? So we're setting this equal to 0. And so that means we're looking for the roots of this construction. And when we do, we solve for it, and we get roots of the imaginary golden ratio, 1 over the imaginary golden ratio, the imaginary golden ratio squared, and 1 over the imaginary golden ratio squared. We get 4 roots. Let's talk about what the...
Each of those can solve for x?
Yes, exactly. So when you put this answer in here, here, and here, you get 0. When you put that answer in here, here, and here at the same time, and add them together, right, you get 0 every time. So these are the things that give you 0, and the only things. You get 4. But what are these things? First thing to note is that it's just one variable. It's the imaginary golden ratio. Okay, here it's 1 over the same thing. Here it's the same thing squared, so using it twice. And here 1 over, using it another twice. So we've got 6 times we're using the imaginary golden ratio to make 4 roots. That's an interesting thing. But here's why. -1 to the 1/2 equals I. That's the symbol we use for that, right? And keep in your mind, the picture for that is we're on the unit circle, and we rotate from 1 to 1 in the other direction. That's I. It means you're connecting logic that's 2-dimensional. And 1 is the one you started with as a reference, and I is the same scale of a reference in exactly the other direction. So I rotates you 90 degrees to here. That's what this symbol is meaning. You can think of it as this way. -1 is a flip. And this means you've gone halfway in the flip. So if you want to draw a different amount, like 1/3, this is the symbol we call the imaginary golden ratio. It means you go just to here instead. And now it would take 1, 2, 3 to flip. 6 to come all the way back around. 3 to flip, 6 to come all the way back around. This guy takes 2 to flip and 4 to come all the way back around. That's the difference. But they're very similar otherwise, right?
Yeah. Here, this equation you have 1 over x plus x. That is the hyperbola?
This is the infinite hyperbola. Yep. It's not quantized. It just goes to infinity. Which means its mass gap goes to 0 too. And so it's the sphere up top and sphere at bottom, and then we're saying that hyperbolic connection still applies to them, which I think is a stretch all the way to infinity. But after we get from the infinite case, we're going to modify to the finite case, which makes much more coherent sense. Only because if you go into infinity, you lose track of what is the shape I'm imagining. Lots of things you can no longer answer. Having a quantized structure, you can answer those things. So. All right, so, yeah.
So another question. So in this limit, right? So when you, so the gap goes to 0, and then the ball goes to infinite, and the curvature, not the curvature, but the inverse. So what happens to the torus? Also, you just get pushed out to
yeah.
Yeah, so it just gets wider So eventually it just becomes the infinite void.
Yeah.
So that's the limit.
That's the limit. Yeah.
Okay.
Yeah. It's just the finite one we can ask a lot more specific questions about. We lose some track of things in that one. But still, this is a great starting point. So we're imagining just that we have the hyperbolic construction, finding that it has 4 roots made up of 6 copies of the imaginary golden ratio. And remember, 6 copies gets you 1, 2, 3, 4, 5, 6. Back to 1, right? 6 imaginary golden ratios is back to 1. So we've closed our unitary cycle, or whatever you want to think of this. We've closed the loop. with 6 pieces. And here, our zeros were made, our roots were made out of those 6 pieces that can close a loop. Okay, to change from infinite to finite, we need this volume not to extend forever, but to wrap around something, to divide about a circle. In other words, we need to be inventing a circular boundary internally that twists the boundary around. And 1 circle is the minimum. You can go up 2 circles, 3 circles, 4 circles, but if you want the minimum one, 1 circle will be the wrap. So we're going to change this equation, which means our roots are going to change. This is the one that applied to the infinite case. But we're going to divide the volume of our construction by 1 circle. It just needs to be internally divided by 1 circle. Okay? And instead of setting this equal to 0 now, we're going to ask where that construction equals the things that need to happen geometrically to quantize under that rotation of 1 circle. Meaning what? The system has to be hyperbolic. It has to fit together so that we rotate and rotate and rotate and close a loop. Right? We're going to rotate in one direction, 90 degrees this way in the plane, and we call that I. But now if we want to go out in this direction, that's another I, which I can represent with a different letter and tell you it's the same thing as a square root of -1, but just in a different direction. Or I can say is I to the I. Okay? So 2 orthogonal rotations, and both of them are going to be separated by another pi over 2, another rotation. So it's really, we're talking about an intersection of a corner here, where you have a rotation and a rotation and a rotation, and you end up exactly where you started. And they're all orthogonal to each other is the point. The wall, and the floor are all orthogonal. That's why it comes back. If they weren't, then it wouldn't close a loop. Okay?
So it's a quarter sphere.
Yeah.
Okay.
Yeah. We're quartering a sphere is a good sentence to have in your head. We're quartering a sphere. We're dividing it internally into 4 boundaries on the inside. We're quartering a sphere. Now, what does that look like? That's what we're getting at. Yeah.
So that representation, the I raised to the I, that's all raised to the negative pi divided by 2.
Uh-huh.
Are there not other ways to write that notation-wise that might be interesting to folks?
E to the negative pi over 2. I to the I think.
Yeah, it ends up being the same.
Yeah.
Cool.
So yeah, I mean, you have to train your eye to notice the characters they're using. Maybe some other ones will be easier to understand than but I'm trying to use the ones that my familiarity can go through this with.
Yeah.
I think I is nice, short, and beautiful, but it's because I have a geometric picture in my head for what it's representing. So I really like this picture. This is a very simple claim here geometrically. We're just saying we're closing under 3 rotations, right? We're a system that's closing under 3 rotations. So they're all orthogonal. I need to qualify that. They're all orthogonal. So there's 3 dimensions involved in that. And then now I just need to care about my mass gap. If we're in this hyperbolic construction, I need to set the scale of my mass gap. In fact, I really should emphasize the scale by doing this. Okay, it's a scaling parameter for the construction of hyperbolic geometry. Remember, this construction itself is general. If you make it wider, you get a torus of a different size. If you make it skinnier, you change how it looks, but this is the stamp of what it means to be hyperbolically balanced. Okay? Now we want to get the exact scale of hyperbolic construction that's applying to reality. So, like we said at the beginning, we're going to put in for the mass gap the Planck mass, the mass boundary that we've observed without explanation for why yet, right? But we've observed to be the limiting value of mass, the biggest piece of mass in all the things that we've seen constructing these 5 dimensions, in all the properties of atoms. Okay? Great. So let's put in M sub P for Planck. And there we go. We've changed from looking for where we're at 0, and now we're changing for looking for where we're flipping. Before we were kind of looking for the other limiting bound. We set it equal to 0. Now we're looking for this construction, right? Exactly this construction with this mass gap and these 2 twists orthogonally inside. So these constants change from what they were when we set this equal to 0 and it didn't have this 2 pi closure to Je1, Je2, Je3, and Je4. Just to find the numeric values of those numbers, you plug in this equation, okay? And they pop out as the roots of this connection. All right, so it becomes really important to try to familiarize yourself with the algebraic claim of this sentence.
So you're saying that you can substitute x with any one of those four?
Mm-hmm. Yep. If you put in x or Je1 in here and here and here in this form of the equation, it would solve this. It would kick out the same number as this.
And the fascinating thing is the first two J's, those are one-dimensional components. Je3 and Je4 are actually two-dimensional components because they actually do have complex additions to them.
Yep. Je1 is real close to 0. Its first digit is 0. And then Je2 is out here on 3. So Je1, Je2. Je3 is in the complex plane, not on the real axis or the imaginary axis. It's out in the area up there. 3. And Je4 is like the mirror image below. Same x position, negative position in x, but opposite positions in y. Okay, these are the points of division under the scale of hyperbolic construction fit to the Planck mass. Okay, if we take hyperbolic construction and use it to fit with this scale, then this is the way things will divide. Now, the really exciting thing that first pops out when realizing you've got a structure that divides this way is that these four constants tell you a lot about the actual geometry of the internal bits, how the pieces are divided about. And if we take Je1 squared, it equals what physicists and chemists know as the fine structure constant, alpha. The fine structure constant is the central mystery, the central known mystery to focus on, that if you can answer what this thing means geometrically, what does it write into the world? Why is that number responsible for chemistry, for the way electrons act, for the size of charge pieces in the world, and so on, right? It's extremely built into all the constants of nature, the equations for physics and the equations for chemistry. It's very fundamental. And here we go, a partition structure where its first piece, squared, gives us the fine structure constant. Why do we care about squared? Well, to help see that, I might leave that a little longer. Let me back off and say, the first thing, if we're partitioning into four different ways, we could ask, what's the sum of those four ways? Just give me all of them together. So this is a doubly interesting thing because I just said sum, and remember we're describing a geometry that makes sense of what sums mean. Remember, make sure I get back to that at the end because I haven't made sense of it yet for you, but it's, the geometry we're talking about is the geometry on which the operations of mathematics work, plus and minus, multiply and divide. That has to mean something in this picture. Okay, but here notice when we take the sum of these four new numbers, the quantized versions, okay, then we get 0. When we take the product, the other one we would immediately want to check. We get that they produce a circle.
Cool.
Well, we kind of knew that already, but that's really nice verification here. We got 4 roots of a hyperbolic quantized construction that together produce a circle. They sum to 0, making a perfect balance, but they produce a circle, making an inversion, making a wrap around to something, okay? Well, we can go one step further that's common here in this sort of mathematics. We're going to go not just for products and sums, but we want to check the quadrants of the roots. The quadrants of the roots is found just by squaring them and adding them together. Je1 squared plus Je2 squared. And this one is equal to negative 4 pi, a projected sphere. Quadrants is the thing you're dividing up. Here we're quadding, we're dividing a sphere 4 ways. And the first piece of the quadrants is the fine structure constant, what we've traditionally called that, which means you could call this one the second fine structure constant, and this one the third, and this one the fourth fine structure constant when they're squared, right? And those 4 fine structure constants are the 4 quadrants pieces of the sphere. I think that's really, really beautiful. That's a starting point. If we keep going, we find that the structure written in just by these constants, by these roots, by these central pieces of how our hyperbolic quantized construction is held together, they give us the quaternion algebra restriction. Now, is that an unfamiliar sentence or familiar?
Not for me.
Not for you, okay. Quaternion algebra means we have a 4-dimensional algebraic system that closes, where all the operations can be exactly coded, perfectly defined, and then they work every time after that. They do things and they can undo them backwards, right? It's a coded logic that you can multiply, then you can divide. You can add, you can subtract. It always comes with its inverse. Okay. The logic that we found for the external world for general relativity is a 4-dimensional quaternion logic. Those are almost the same thing. If it's 4-dimensional closed division algebra, then it's the quaternion logic. There's only one option. Okay, you can also have closed division algebras on 2 dimensions. Just be on this one sheet, and it still all works. And if you just look at 1 dimension along that sheet, it'll still all work because it works everywhere in the 2 dimensions. So you can have a closed division algebra where operations work in 1 dimension, in 2 dimensions, in 4 dimensions. If you go more than this sheet, you have to include the whole other sheet. Okay, you can't go to 3 dimensions and close your algebra. You can do it in 4, you can do it in 8, and then you're done. You can't get a division algebra, you can't get a closed partitioned system that can balance under perfect inversion, closing itself using just its parts, not being injected by energy from the outside. You can only do it down to 8. After that, they're not available in logic. If you go to the next step, to 16, you lose some of the properties of a closed division algebra. So we know why. You actually lose the ability to close yourself. Your parts don't become similar enough to swap them out just right and say the whole system's perfect now. Yeah, so you can have a balance defined in 1, 2, 4, and 8 dimensions. And our structure, the internal thing is a hyperbolic figure 8 knot, right? And that's balanced under 8-dimensional logic. Logic, not pieces, 44 pieces balanced under 8-dimensional logic. So it closes under 8-dimensional exchange, known as the octonian logic. Outside, things have been twisted and looped once, but now we connect under this 4-dimensional logic. By the time we get all the way out to this scale, we're connected under 4-dimensional logic. Okay? And that's where we're mostly focusing because we're coming from the outside and trying to go in and see the whole picture. But remember, when we're done, we should be able to go around from the bottom and go step by step by step up, out in scales of balanced logical systems, go out to the next one, until we get all the way out to the sphere again. Okay. So we've got an internal peek now at more of the internal structure. These equations, which have answers we can readily get familiar with or comfortable with, right? That we know what it's telling you here. These pieces now tell you the way that the parts of this decomposition keep their symmetries, the way they're held together. And if we kept going with the equations as we wrote down, we'd see that if we go up to Gr to the 4th scale, Gr to the 4th is held together under quaternion logic. In fact, the algebraic equations you can write down from this set of 4 parameters goes up to power 4 under closed logic, and that closed logic is forced to be a quaternion system. This is really beautiful. I'm not saying if I'm conveying it completely to you, but this naturally happened. So this is really, really cool. The algebraic structure being built in under torus symmetry gives you all of Clifford algebra. The scaling parameter tells you exactly what size of hyperbolic structure we're using. So now we know all the bits and details from the whole sphere all the way down to this scale of exchange making our first torus. Where are we going to go next? So we got a story where we're putting together geometric pictures of a geometric balance of a projected system, right? The clues that we're going to rely on have to come from the measurements of the constants of nature. So now we need to turn to investigating the constants of nature. First step of that is to go to the CODATA website. Okay, if you've never done it before, spend a day geeking out on the constants of nature because they're the details that describe your fundamental reality. To the brightest minds so far throughout the whole reach of history have come to a conclusion that those are the fundamental ingredients. So they deserve your attention. Right? In fact, more so, they deserve your attempt to make sense of them. Because as we collectively do, we gain powers we couldn't imagine before. And let's face it, we're in need of some of those right now. We're in need to get rid of the yoke of money so that everyone can become a different kind of human that doesn't bicker about power and control and reputation. Instead is invested in conversations internally about learning more, about seeing more of the reality around them. It's much more fulfilling. Anyway, rant over. All right, the constants of nature are the next step. So you look up the CODATA constants, okay? Scroll through them. Just start getting used to some of the symbols and the words. You've heard electron charge before. You've heard a couple of them. But notice how many there are. They're listing all of the chemistry and physics ones. By that I specifically mean these are considered fundamental parameters because the physics ones are the smallest pieces, and you can use the small pieces to put together and make other next step pieces like Lego blocks, and they're including all of those. So there's two levels of information there and a lot of data points, but it's all given to you in just numbers with dimensions at the end. That's our starting position. So we have reported facts of the world that we have to make sense of from numbers. We have no other choice. That's how they're reported. That's the only way we know the content of these things is through the numbers they have, okay? And the dimensions. So, first thing is, we have no guess how to interpret the numbers. So let's move to the dimensions. The dimensions of any constant. I really need to make space now. So, is this picture starting to help? Okay. Then I will erase it. Oh.
We're using our modern magical technology to record it, so we can
Yep.
go back to it later.
Yep. So what's changed from the last time I made a public video on this was that before we had a data set of 44 constants of nature for physics, right? And we were interpreting them using the method we're about to go through in one example. But that data set was only at 44, the fundamental bottom ones that you can build all the connections with too. Now I moved on to investigating the rest of the set at CODATA. So the chemistry, what I'm calling the chemistry ones too. It's a bit fuzzy because they do physics things also, but if they're composite, I'll call them chemistry. If they're fundamental pieces, then I'll call them physics, just to make it easy to talk about. All right. When we look at a constant reported to us like this, I put this symbol here to mean that CODATA has picked this as one of the ones to make the reference for the dimensions themselves. They just have a set that they pick and they assume those are the ones that are correct, and then everything else has to be defined in reference to the dimensions that those claim, right? And it's a tricky game. It's difficult. You need better measurements by far to be able to be more confident in the way you're making those definitions, but they have to do the best they can. So here, the speed of light. Speed of light is 299,792,458 times 10 to the 8 meters per second, 2.99. So traditionally we put one significant digit and then a point, and then keep going from there how many we have. A lot of constants, instead of being the reference, they'll have error bars. So they might have gone 4, 5, 8 with an error of 1, 2, which means the last 5 and 8 have a plus or minus ignorance of 12 to them. This is the best guess from the measurement, but the known error in the measurement shows that, but we're only confident plus or minus 12 here. Okay. The speed of light's an exception in that case. It's one of the ones we use directly for the definitions of the dimensions of meters and seconds, which are reported here. So what we're saying is that the bases of measure for time, space, charge, mass, and temperature all have to have scaled units that we give them. The same reason that the hyperbolic space we picked had to have a scale. That once you pick a scale for that, the smaller pieces of decomposition have all been picked. Okay? But here we have meters and seconds with the unit that we're going to scientifically attach to the meaning of distance for meters and duration through time for seconds. Okay? So in science right now, the meter may have come from a historical, well, especially over here in America, we think, oh, the foot, that's the base for measure. And we all know that that's just made up. So it's easy to think that when you move to the meter, it's just made up too. It was just some guy's arm length or something, and then we fixed. No, the definition for the meter and for the second and for the coulomb, for the 5 bases of reality, the 5 kinds of things you can measure, we're getting those definitions from the constants of nature. We're getting them from that. This number is written in as a relationship that's held by the best bases we can define for length and time. There's a scaling parameter connecting those 2 bases, okay, known as the speed of light. And this is going to then code for you what happens at the speed of light, or we know how to interpret speed. But the point is, we're going to break it down to every component of its dimensions. Okay, we're going to try to see each constant of nature as a relationship between dimensions. And the number is telling you how much you scale when you interact these 2 dimensions. In this case, it's just 2. Okay. So you go to the Codata website, or just type in Codata, and it'll immediately take you there. And then you can start clicking on different constants. They have them organized into different piles, so you can start familiarizing yourself with them. Or you can just go to the entire list, okay, and start looking at all there are. Notice all of them are numbers reported in base 10. All of them will have a power. Maybe the power is 1, but they all have base 10 powers, and they all represent just the 5 dimensions in relationship. So the dimensions are limited just to the 5 base kinds, right? So, yeah.
Yeah, so actually a related question to the earlier the discussion. So let's say when people pick meter or second or kilogram, right? So these are like what we consider SI units, right?
Mm-hmm, mm-hmm.
I thought like there are some arbitrariness to it. So what if like we just happen to pick the meter that is like 1.5 times what we currently define as a meter, right? Or just like you see what I mean? So what if we pick a different?
Let me try to be really clear about it. You can pick any of the 5 bases and talk about a feature of mass, or talk about a feature of length, and not talk about the other 4 things related to whatever the thing you're talking about, right? Just talk about one dimension at a time, and any scale or any base works to do the job just the same.
Yeah.
The point is, in nature, in the structure of atomic matter, there are 5 bases written in, and we're actually in science, around the world we have all kinds of bases people familiarly use. But in science, we're honing in on definitions of bases that give us sharper and sharper pictures of the constants of nature themselves.
Sure. Yeah. So the question is.
So there is a little bit of wiggle room at the end, right? The meter itself is definitely the best representation of length according to the patterns of nature out to the scales we understand it. But then there's an error bar, and you could swing the definition of the meter within that error bar and still be, to the best we know, correct. Yeah.
So the question I want to ask is, so let's say the Planck length is a fundamental, like a length scale, right? So that is just a fundamental to the geometry of the universe itself. So if you measure everything length using Planck length, and then you only have one number, like or some like how many number of units, right? So for Planck length for this height of the cup, right?
Yeah.
So, but if you do it in meter or like whatever the foot, right? So, and then you would get a series of number that depend on the unit.
Yes.
Right, that you pick.
Yes.
Right?
Absolutely.
Right, and then so that means.
And it'd be a different number if you change the base.
Yeah. So even if you keep the base 10, but the series of digits and the power, right? The scale, the power could be different depending on what if I use a mile to measure the cup, right? So I might be off by 3.
Yep.
So with that, then I guess the question is, can you still look at the digit one by one, and then sort of interpret it in a way that's like that we discussed the other days, like then you go down to the fundamental scale and say, so these are the partitions, or like how you like go layer by layer.
Are you asking, could you interpret the balance of the constants of nature in other bases and still find the pattern?
Right.
Still find a pattern?
Let me try it another way. So right now the speed of light is 2.99, 792, 458. And that is expressed in the unit of meter divided by second.
Mhm.
But what if I write it in the foot per second?
Then it's a different number.
Yeah, it's a different number.
And it's also not a constant of nature.
It's not a constant.
It's definitely not a constant of
Right,
nature if you
because
write
it
it
would
in
be arbitrary.
feet per second. Because the constants of nature are in reference to just the coherent system of units. They're referencing the patterns existing in the bases of reality, which we don't know what are, but we know they're real. They're measurable. So they're the most real things there are.
Yeah, I think basically the way I like to think about it, and correct me if I'm wrong, but basically the dimensions of measure are essentially, those are ingredients, and then the corresponding numbers we have are the magnitudes. And basically what I'm hearing from that is basically the reason why we use SI, basically more or less the metric system, is essentially because it is a coherent set of units.
If you report to me the number of the speed of light in feet per hour, you're not telling me a constant of nature. I think that's a thing to try to make it as a clear point. You're telling me something that could be converted in a certain way and get to that constant of nature, but the constant of nature is reporting to us a built-in feature of the bases of reality that we don't pick, that aren't picked by us.
So I think in this case, so the speed of light in these digits are unique because you could also, instead of writing meter per second, you could write it in Planck length divided by Planck time, right?
Yes.
So therefore,
yes.
That's a constant of nature.
How about this? This will help. I'm not going to cut you off. We'll continue. But the Planck time, can you look at the number at the back and read the number to me? The Planck time equals...
Planck time is 5.3912583682. Excuse me, 832313.
All right, let's think of this. Times 10 to the negative 44 seconds. If you take 1 over this number... Oh, wait till he's back. This was for him specifically. All right, so this is the value for the Planck time, right? Now, I want you to see exactly what this is claiming is happening. A base, a dimension, is a thing that divides 1. We're thinking of 1 as the whole projection of the sphere made by this thing, but even just mathematically, simply 1, if you could divide 1 by something, that thing counts as a base. Okay? We have a base, a measure that's dividing 1, the projection, which means if you take 1 over this number, you get a big number. What does that number represent? The number of pieces that we've divided the domain into at that scale. Exactly. The number of pieces that the universe has, our simplest universe has in it, when we've taken the energy of the boundary at this scale, and then it's broken into smaller eddies, and then smaller eddies, and smaller eddies. The smallest eddies at the bottom have this count, 1 over this count, for the number of them. That's a big number. That's the base field on which everything happens. Good thing it's a big number. That's the base of time. It's composed of that many copies of itself. My point is that relationship here is where we're getting the definition of this from. That's what we mean by seconds in science. We don't mean an arbitrary one, reference that a king picked somewhere. We mean we're changing this reference all the time based on the constants, but ultimately that's where this thing comes from. It's a dimension that divides 1. It's a dimension that divides 1 into what? Into 1 over this number of pieces. Right? It does that exact amount.
Well, but wasn't this just a lot of based upon basically just quantum mechanics and like just H itself, just Planck constant?
Well, yeah, Planck constant help us get to the definition for seconds and so on, yes. Yeah. But so looking into these numbers for patterns is extremely rewarding, right? Because that's a piece of clarity. We're starting with a base that projects into a quiet, boring sphere on the outside, but it's held up at first glance with just a torus boundary that has this cone-on-cone balance that it puts into the system, right? Its boundaries divide that way, just like under hyperbolic four-dimensional construction. But as we go inside and inside and look at just smaller and smaller regions, so we're ignoring the dynamics on bigger scales, right? We're zooming in on it. Then we break up the system into the 5 different number of actions. And each action comes with an exact number of pieces that it's breaking the system into. I think that's pretty cool. It's a giant number, but it's an exact meaning for what the number is. Okay, so think of that as the base field that's available for flips to happen, for changes to happen. And the next size field on top of that is going to be the space field, right? And there's 10 to the 35 places to put flips there. And so
Time is the first flip?
time is the smallest field there is. Yep. It has the most number of parts making that field. And space is less numbered, but bigger in scale. Once you make your smallest loop, the smallest thing in the field will be the time loops, right? So say we've got a time loop. We've got one circle we've made of some size. These things are going to be what we make references, or the dimensions reference anyway, but if we have a thing on that scale, we can have another one. Great, now we have two. Two of the same thing though, we're just going up in count. We didn't get a new essence of closure, a new place where the logic does a circle or closes a loop. Okay. In order to get that, we need to get out to the point where we have 6 circles. These are all supposed to be the same size. 6 circles surrounding the first circle, all the same size, but now they combine to define another sized circle. Already you can kind of see some torus shape here, right? But the next circle that's compatible with the first, building the world from the first ones, is this size. So this is going to be the size of closure of the loop in the space field. And this is the size of the closure of the loop in the time field. So there's a 7-to-1 exchange between the space and the time closures in the balance. Okay? That becomes important because now we want to say, well, the first loop of time, when you make this system, you don't just break into a mass boundary and then later wave propagates and break into a charge boundary and then waves propagate. You get everything all at once so you don't get it. The whole system is a manifold. So you break into the time boundary, you've also on the other scales broken into the other boundaries.
Can you go over that one more time, maybe using slightly different words, just for clarity?
This one?
Yes.
All right, so we're just imagining abstractly that we've got a smallest loop. So we formed a smallest loop, and we're going to call that our time loop, okay? But if we want to build other closed loops, persistent properties need to be properties that do something, but eventually come back to their first state and then do the thing again over and over and over and over. Every new possible expression you can do under closure becomes a new persistent property, right? So this thing is the first persistent property. A circle of some form comes into existence. Now, since it's the only one around, you want to build the world from it until you have other ingredients to include. But ingredients need to be things that maintain what was there before, or the things you're adding, but maintain them under closed logic, under a balance, right? They need to loop something up again. So the next loop we can get was the construction of just the smallest ones. It requires we go out in scale. Maybe you've never noticed, but if you take circles of the same size, 6 of them perfectly touch each other, right? And the inside one. And just fit it like that. So that's the fitting together, natural fitting together of circles. We build a second scale of the construction, and on that scale, we can get another closed expression of the balance. It's a different expression. It's tied to it. You can't change the other one without it changing, but it's still a different expression of the balance. Okay, so that 7 scaling parameter needs to close at the second step against the base construction. And the base construction is just the breaking into 5 dimensions. Okay, the time dimension closes a loop in all 5 of the dimensions. In fact, the time dimension is touched. There's a loop that goes through all 5 of the other expressions. Okay, they're not, except for a few places where it gets kinked out, like in a black hole. Otherwise, it's there everywhere. It's in the construction of everything that's built at the bottom. Okay. Did that help more, or you got a question on this one?
I'm trying to gain a little bit more intuition rather than it just works, but more why it happens to work.
Yeah, okay. Well, the thing I want you to keep in mind for why is that, first of all, there's a built-in preference for constructing and scale of 7 up if you're making things from circles. So that scaling of 7 is part of the answer for why. The next part is, after you've scaled up on that size, and you've got the actions on the smaller size, what's the exact shape in which you're closing the larger scale? You close the smallest scale on the small circles. But what's the shape of this closure on the second scale? Okay, and for that we need to go into the equations that we're using for the Planck constants. But before we do that, I think I lost track of where I was going to go on that.
7 to 1.
7 to 1 in the base 10. Yeah. Before we do that, I want to say that we're starting out with a base 5 system that we're claiming is the hyperbolic figure 8 knot on the inside. That base 5 deranges 44 ways, but it also self-closes, right? It's going to wrap back on itself. So if you go through the base 5 and then go through them again, you're back at the loop. You're doing it again and doing it again, doing it again and doing it again. So there's 10 exchanges for you to go through to cycle through every action in the closed loop formed at the bottom. Kind of follow that?
It almost sounds like if you have an empty universe and only introduce time, that would cause the Big Bang. I know it's kind of a leap.
Yeah, no. I am saying that if you have empty of form, there's no structure that you can point to in it, and you make the smallest loop at the bottom, when you've done that, you've necessarily, in order for it to keep looping, there has to be all the counter things acting. And the whole collection of our minimal universe is required for just one piece to happen. It's a very complex gearwork system because it's cascading the scales, right? But yes, I'm saying if you do form the one, then the rest should come too. Yeah. Okay, so the big point is there, that's saying that at the base, we have to go through 10 possible things. There's a string of 10 that loops. There's a base 10 written into the balance of this double cover at the bottom because it's ultimately creating 5 bases, but it has the other restriction of being self-closed. So the 5 bases have to be used against themselves to repeat and repeat and repeat. So this gives us a distinction of base 10 that we care about in the geometric structure. It's not because we have 10 fingers. In this case, we're caring because we have a base 5 double cover that's we're treating as base 10. Now, that's on the smallest scale. We care about a base 10 pattern. On the next scale up, that pattern has to close using the base 10. It's already in place. How can it do it? Well, remember with the scaling of 7? We're going to use 7 and 7 instead of 5 and 5, but we're going to use 7 string of digits instead of 7 string of digits. We're going to put it together in the string of the base 10 string. The pattern is going to be carried but closes. At 14 digits, we now have another pattern that closes the quantized structure of the whole thing, right? So this is how I understand this right now. This, to me, those words bring a lot of clarity. I don't know if it did to you, but it really helps to see you're actually claiming a geometry that breaks into whole numbers of pieces of things. And at the base, the balance is 10 bases, or it has a base of 10. Right? And then the base, through the logic as you go up, actually changes. The most relevant base to your domain depends on the scale you're at. But if you're at the bottom scale, base 10 is what's holding it all together. So there are going to be other bases that make patterns perfectly revealable in the system, right? Base 7 is going to show up as a thing. Base 5 should have important things. Base 2 is going to be important. Base 18 for charge. Base 8 for mass. They're all going to show up, but all of them are going to be holding with a pattern at the base 10 at the bottom, because they're all linked at the very bottom with a time loop. Okay, the smallest one that has the base 10 in it. So it's a dance of bases in a way, but the easiest way for me at this point to conceive it is to do it and frame it in terms of the bottom base. Base 10, that gives us our number system. You can go 0 through 9 in each of the digits, but there's 14 digits because that's where the next closure in the 0 through 9 strings come. Make sense? Okay. I'm saying that you can find patterns in nature that will be in base 18, and those will be the charge patterns. Okay. You can find mass patterns in base 8, but if you want to look for all of the patterns that connect them all, it's base 10.
Really?
They're at the bottom.
Oh.
Yeah, that's the clock of the computer. Everything's going to depend on the tick of the computer, and it's composed at most of the most tight intersection of 5 different kinds of circles. And both of those circles have 2 parts that they play. The role on the inside of a torus and the outside of a torus. There's 2 bits of information from all 5, so that's a base 10 composite logic at the bottom.
Oh, that's incredibly convenient.
Yeah. Yes, it is, because now all the numbers that are reported to us in base 10 can be attempted to be literally understood. Not just the scale that these 2 have in relation, right? That's all I was seeing before. Now we can look at the individual digits and they will mean something. They will mean something about how the 5 boundaries come together through that string of 10 things that cycle. Very interesting.
So that goes back to why we're using this system of units, why it happens to work, and why, rather than necessarily just doing a foot in an hour, this makes even more sense.
No matter what base you would have picked, if you found a pattern written in, you'd be like, wow. So far in science, what we do is we report numbers in base 10, and we found there's an extreme fixed, completely known to many digits, almost up to 14 in some cases, right? Pattern written in, and that's the pattern we're trying to understand. So it is part of the fundamental mystery. Why base 10? Until recently, I didn't really realize to these many words why, but it's fundamentally just because we're at a hyperbolic figure 8 knot. That's a double cover of 5 actions. Yeah, and that's the smallest closed logic. And they have different scales of closed logic, but they include the scale that they're on. If we want to be universal to all, time is the base of them all. Okay, now we've already gone through many, many hours and days going through constants, crunching numbers on Wolfram Alpha and so on. I don't know if that's what we want to do next. I just wanted to mostly give an review of where we're at. But now let's finish off with the picture. So we have a universe that we're saying we can minimally construct from a random infinite void to make a cage of balanced logic. And that cage on the outside becomes just the projected limit of the dance of boundaries on the inside, making a spherical, quiet boundary. Two-dimensional surface that nothing happens on, and just inside that, everything agrees to a certain kind of logic. Okay? And then we're interested in detailing out exactly what that logic, or exactly the boundaries that are formed in the decomposition as we go in scales. And as we zoom in, the first thing we see we zoom into the universe, and the first thing we see is a torus on some scale. Okay, it has a center here. We're zooming from the projection. Then that torus has a thickness that's non-zero. But at first, you would think if all this is fluid, then there's like a hurricane wall holding itself up, just here persisting. And it's not all that magical, it's just floating on itself, but it's what's balancing all the pressure of everything on top, right? That's the counter, the invention of these boundaries. Now, the inversion cone between the boundaries is still there, okay? I'm going to zoom in now on this one and find out that it's actually made out of rings. I need to draw the rings that go all the way around to be Hopf-links. But when you zoom in, you notice that it's actually composed of rings stacked together to make that shape. So the surface of the boundary went from being, in your mind, a smooth torus, like a donut shape, to gaining more texture, okay? Meaning it wraps around with another feature in it, being a collection of rings. And all those rings are Hopf connected. So each ring goes through every other ring once. So they stay in cohesion balance with each other. Okay. Ultimately, what we're doing right now is we're decoding the Hopf map. We're trying to get a picture of the Hopf map. And what is it? It's a map between the 3-sphere to the 4-dimensional hypersphere. Okay? The place where we're cone on cone exchanging. It's a map between how all that happens. And this is what we're trying to explain now. So as we zoom in from the first boundary formed, on any of its parts, we can look in closely and it's made up of a ring, smaller rings collected. If we zoom into any of one of those smaller rings, it's got another number of rings, and every time it's going to be a whole number of rings. They'll all be connected in the Hopf way. There'll be different sizes though, right? They'll all be the same size as each other in one ring, but every time we zoom in, a different size of ring is introduced. Okay, stepping all the way through the scales, we just go from set of rings to set of rings to set of rings to set of rings through the torus construction. So if you distort this surface, if you distort this universe in any way, the energy content in it will be able to disperse its boundaries in a way that goes from down rings, down rings, down rings, down rings, and gives more distorted surface area, or smooth back out by taking less energy. Follow me? Distortions could follow down the scales that way. So the shape of the boundary goes from smooth torus to more rigid with rings and more rigid with rings, just like we do in a fractal construction. Okay, that's the picture, except for it doesn't go forever. And I haven't given you details of how many numbers of rings in each step. We have to fill in that exactly to get the whole picture. So let's go all the way to the bottom of this. It doesn't go to infinity. And we have a hole at the bottom in the shape of the hyperbolic figure 8 knot. Okay? And that, as we go out, is held together with the next feature, making a closed torus. And as we go out to the next feature, what is the next feature? We add one more Geeskian manifold. Okay, the hyperbolic figure eight knot has one, and then wrapped on itself two Geeskian manifolds. We add another Geeskian manifold into the metric. Okay, then we go count to 3, and then 4, and 5, and 6. We can keep adding another. We can keep adding. It's going out in the sense that the boundaries all now it's not out this way. It's 1, and now 2, and a 3, and blah, 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 out like bubbles. Okay, they stay in focus in the center, but yes. Okay, so we can add to this structure in whole counts of Geeskian manifolds. Why? Because at the very bottom, everything's maintaining the logic of the Geeskian manifold, right? That's the fix of the whole thing. So we can keep adding distortions and counts of that. And every time you do, though, you have to have a new set of wave dynamics that take on a new torus construction on a different scale, a new set of rotations that make a new torus balance. So there's a new torus in reality on that scale. Now, every time you add one more, you get another torus. But every time the number happens to be a prime number that you're landing on in the count, so you get to number 7, you'll get another Geeskian manifold. You added the 7th Geeskian manifold, and that will have a closure. But because it's prime, there will be a second closure that comes in magically for free. There's another unique feature, another torus balance, put into the metric using its already present parts at that scale. Okay, so every prime number introduces another new feature that's not just the trivial new feature of copy 1, 1, 1, 1, 1. Okay, I really, really love that connection. I don't know how much it was clear in your heads because I'm just using words and not animations, but.
Now, is that second feature, does that come in on the same scale or a different scale?
It counts features on two different ways. We can count via primes and we can count via plus ones. And as you count plus ones, it's like, okay, every plus one I got a new feature, every plus one I got a new feature. But when you get to the number that's a prime, I got a new feature and another one. I got 2 features this time. Yeah. So this is really, really fundamental connections to number theory and ways to think of numbers. But primes themselves were supposed to be representatives of indivisible things other than by one in themselves. So that represents, other than in the count by one way, a new element in the numbers, right? A new thing that can't be divided and made up of other smaller things. And that's a new feature. Same thing with this story. We're counting up in construction using toric construction, toric construction, toric construction at every scale up. And it's going to not be exactly the same as you scale up transfer from each one, but only because you're transferring from a different number of tori in the rings to a different number of tori in the rings. If it was always the same number as you went, it would look exactly the same in every transfer scale. All right, I think I have put the picture out there where I'm at right now. Oh, I should also throw in a few other pitches for the projects I consider important that I need people's help with. Okay, one project is, Tony helped me a lot yesterday understanding how we can use GPT to get past my own ignorance in programming and so on. So that's going to be very helpful. But the projects I want to complete, number one priority, make an accurate, very visually accessible animation of the geometry we're talking about, of the fractal connections between every of its finite number of scales, so that someone can build their intuition by going through the animation, either by watching a video or maybe just moving through themselves, right, and seeing what the structure looks like. Have it color coded so we can see the bits and parts moving, right, but to get familiar with how these boundaries exist on different levels. Because once we understand those boundaries and you have a picture in your head for what they're doing, you immediately start coming up with ways to intersect with them, to use them, to do things with them, to test things with them, to ask new questions. So that visual to me is the priority. That's what's going to help more people throughout all of history have a better interface with the topic, right? Having a clearer picture. So that's the goal. And I think we've said in words a picture enough that you've at least got an image of how we're zooming in fractally from scale to scale through the torus connections, and that there's a limit, and that limit makes sense, and the outer limit makes sense. But now we need to make a clear sense by having an accurate animation through all the scales in between. Okay? And then I really think a lot of things are going to start happening. When the picture in your head starts matching the features of reality, you can use the clock's gears. So that's one major goal. Part of that is I want to be able to parse the individual boundaries. So we have an equation for the Planck times balance, the hyperbolic balance that's cutting off the Planck time. It gives a gorgeous picture. But to get familiar with that picture of how it's dividing the world up into this hyperbolic figure eight knotness, you really want to spend time zooming out in scale and zooming in scale, zooming to different places like you would on the Mandelbrot set. You want to get familiar by becoming familiarized with all of its different features. And that's to me a big priority, but to do it for all 5. So once we figure out how to code it for one, it should be pretty easy to code for the other ones. But I want to pre-tweak really interesting parts for you to look into and make some videos on that. I think that'll help a lot. Another one is automatizing the search process so that people who aren't willing to spend 8 hours a day trying to get 1 or 2 answers to a math question can do it in 25 seconds and then continue that process. It's a lot more inviting, right? You have to find treasures so often in order to be able to continue being excited by it. So if we can bring that threshold down and make more people get to pour their excitement into this progress, we'll make even more insights. So those are basically my goals. I want to learn how to do those things myself, but if anybody knows how to do them as an expert and can write the code and send it to me, I will learn that code. It'll speed me up, but that's where I'm at basically. I'm also going to be spending all my time until I finish the rest of the constants. I'm going to try to go through the rest of the data points so I have the full set of clues to the best I could find, and then whatever ones don't match up in the pattern, let's second guess them. Try them again, see if you can find an answer that fits this pattern that we found between the rest. That's where I'm at, and we're making phenomenal progress on that. It's really, really patterning up. In fact, one thing I want to say is in this structure, the fractal structure, you're going to find that on every scale, there's going to be repeats of things. Because there's whole numbers of tori in the bound, so there's going to be repeats in how things connect. In the whole poster of the chemistry constants, you can very quickly see that there's whole repeats of a connection, algebraic arrangement in things stamped into nature on a certain, say, on the mass scale. Scale up in mass, all these different mass particles have the same arrangement. So over and over and over, it's like having the elephant trunks in the Mandelbrot set go down in scale, but it's the same sort of pattern over and over. Yeah. Anyway, that's where we're at. That's what we're starting to see come together. Our ultimate goal, remember, is to make a universal replicator, a machine that every individual on the planet can have free access for the rest of their life to local transfer of energy. No more communication from around the world to get the products you need. No more waste of all the transportation. No more hierarchies of trying to control it. Every person can directly take dirt and get food. And that's going to change things a lot. Whether it takes us 1,000 years or we do it in 50, it's going to really change things. So I vote we try to make it in 50. It's the kind of life I think that everybody would prosper more in, mostly because it invites the internal question process far more. Right? If you're free up to not say, oh, I can't because of money, you come up with an idea. I want to make a ship and see if it floats. As a kid, you come up with all those ideas, but you stopped because you didn't know how to get the stuff to do it. Right? That's going to change a lot of the investigation process throughout growing up. And I think hopefully it makes it so that we don't stop growing up.